So far, all of the systems that we've looked at, if they have a chirality center at all, have only one. But it's not uncommon for molecules to have more than one chirality center. We'll talk about that in this video. So our learning goals here are how to quantify the total number of stereoisomers that we might have if we have n, some number larger than one, chirality centers. In order to keep all of this straight, we need to have some labels for the different handedness, or how to distinguish the different enantiomers from one another. And for this, we use R and S labels that were proposed by Kahn, Ingold, and Prelog. Okay, the Kahn, Ingold, Prelog labels R and S distinguish these stereoisomers or enantiomers from one another. The way they do their labeling is they list the groups that are attached to a tetrahedral carbon. There are 4 different groups, and they're going to prioritize them using a fixed criteria. The criteria is actually usually the mass of the group, but it sometimes gets a little tricky when there are 2 groups that have the same mass. But anyway, once they have prioritized that order, so 1, 2, 3, and 4, they now arrange that chirality center so they are looking down the bond to the lowest priority one. Looking down that lowest priority bond, they then look at the order of the others in priority order and determine if they are arranged in a clockwise fashion or in a counterclockwise fashion. If it's clockwise, then they give it the label R. If it's counterclockwise, they give it the label S. So this is what it looks like in practice. So here are 2 chirality-centered carbons, and we're looking down the bond to the lowest priority or 4th priority group that's attached to these carbons. In the first case, the first 3 priorities are arranged like this, and we can see that as we go around from 1 to 2 to 3, we're moving in a clockwise fashion, so this would get an R label. In the other one, we have them arranged in this order. And now when we go from 1 to 2 to 3, it's a counterclockwise direction, so we label it as S. Now I've fancifully put a right-hand label and a left-hand label on these just to emphasize the point that these 2 enantiomers are stereoisomers. They are not superimposable, and the R and S labels can unambiguously distinguish them once you know what that Kahn, Ingold, Prelog scheme is for attaching those labels. So we have a way of actually specifying which of the enantiomers we have. Now let's take a look at what happens when we have multiple chirality centers in a molecule. So let's say our molecule has up to n. In fact, some biological molecules have many, many dozens of chirality centers. Well, let's start by organizing these according to how many chirality centers they have. With just one center, we can either have an R or an S enantiomer. So there are 2 isomers that are possible. These 2 isomers happen to be enantiomers. We'll give them hands. Now what if we have 2 centers? So now we can have 2 R's, we can have an R and S, we can have their mirror images, which would be an S and an R, or we could have 2 S's. So there are a total of 4 different isomers. Now notice we've specified these 4 because the R of one is not equivalent to the R of the other chirality center. So in other words, these are 4 distinct molecules, none of them superimposable on the others. What if we had 3? Well, now we have even more possibilities. We can have RRR, RRS, we can have RSR or RSS. Notice that R is the first label in all of these schemes. We can then have all of the schemes which have S as the first label in the scheme. So there's a total of 8 isomers in this case. All right, we could keep going, but I think you're beginning to get the idea that the number of isomers increases as we increase the number of chirality centers in the molecule. So how can we characterize the total number? Well, for 1 chirality center we had 2 isomers. For 2 chirality centers we had 4. For 3 chirality centers we had 8. Are you beginning to see the pattern? All right, indeed, if we have n chirality centers, we have 2 to the n stereoisomers. All right, so if we had 10 chirality centers, we would have 2 to the 10th stereoisomers. Each stereoisomer has only one enantiomer, one mirror image. The other stereoisomers are not enantiomers of that particular molecule. They have a different sort of relationship with it. This is something that we'll take up in a later lesson. So now as an activity, what I'd like to do is propose that you're given a molecule with 11 chirality centers, and you want to figure out how many stereoisomers does it have and how many of those stereoisomers are enantiomers of that molecule. So why don't you pause the video and take a few minutes to think about this, and we'll come back. All right, have you analyzed your 11 chirality center molecule? Well, you should get that it has 2 to the 11th, or 2 times 2 times 2 times 2 times 2, and so forth, or 2,048 stereoisomers. So there are a lot of different isomers that you can create when you have this many chirality centers. How many of them are enantiomers? Only one, and that's all you need to know.